Hello again, statistics students. Our last lecture on new material is a good one. Regression and correlation analysis is our topic today. All right, so as always, we start with an illustrative example. So on page 31, number 1. Suppose it's 6 years now and you finally completed your bachelor's degree in business. Let's be optimistic. Let's go out on a limb. And suppose it's 6 years from now and we finally completed the BA. Further, let's go further out on a limb and assume that we found a job not working for a relative. And this job is a custom manufacturer of automobile license plate holders. You know, those vanity things that you get to go on your vanity plate. There are currently 2 weeks backlog of customer orders. The boss asked you to estimate the production cost next week to assure we have sufficient funds available to cover our operations. You immediately say, oh yeah, I remember something like that in statistics. You go back and get your notes and you collect a sample. Collect a sample of the production costs for the last 30 weeks. And you also take a look at the quantity you produced over those last 30 weeks. And I've supplied that data for you on page 32. On page 32 is the data. So I produced 5,000 units. These are in thousands, and it cost me $14,800. And I produced 3,000 units. It cost me $7,500, and so on for the last 30 weeks. And so you ask me to forecast the cost of production next week. Well, right now, the only way I know how to do it is to add up all of the costs next week, which are my Y's here, and find that the average is $9,000 is the average cost per week. And right now that'd be my best guess as to how much money I needed next week. The average production quantity is around 3,000 units, and we need $9,000. What's our scheduled production next week? Oh, it's 4,500 units. It's a much higher production than normal. Do I think there's a relationship between the quantity I produce and the cost of production? Well, yeah, more material, more labor, more cost. If I was going to produce 3,000 units, I'd guess $9,000 was needed, but I'm going to produce a much higher amount than typical. I need a method to guess at how much I need. Welcome in linear regression analysis. Linear means we're fitting a straight line to the data. Here's the data. I plotted it. It's called a scatter diagram. I got an X and a Y axis here. And we look at it. Is there an exact relationship between the quantity we produce and the cost of production? No. All the points are not dead nuts on the line. If they were, that would be a perfect linear relationship. We'd have a perfect predictor. We don't. But do the points cluster around the line? Yes, they do. I have a pretty good predictor, okay? And where is 4.5? It's over here somewhere, right? So I'm gonna be predicting a lot more money's needed than just the $9,000. I'm gonna be over here, you know, somewhere around 12 grand is what I'm going to guess. So it is, because of the scatter diagram, we think there's a straight line between these two variables. Okay, also accounting theory says what? Total cost equals fixed cost plus the variable cost per unit times the quantity produced. What's the fixed cost? It's the intercept of this line. It's the constant. What is the variable cost per unit? It is the slope, the tilt of this line. So accounting theory also says that a linear relationship probably exists between these two variables. All right, so we think there's a linear relationship, so we go to XL and run linear regression between these two variables. And we get this result. And this is all we have to learn from regression, is the interpretation of the XL printout. So step one, find any variables that we think are related to what we're trying to predict. Step two, run linear regression on Excel. That's what you're going to be doing on the case study. Next, step three, go to the p-value column. P-value, we discussed that sometime this semester. When was it? 20 minutes ago, when we talked about hypothesis testing. And the p-value is how certain we are, that we can prove something. So if we got a really small value, it means what? We proved something. We proved something. Okay. So that's a pretty small value, right? Is that a pretty small value? Looks weird, doesn't it? 5.23 e to the minus 8. Why does XL do that to you? I don't know. What that means is, what? Scientific notation? Move the decimal 8 places to the left. It's 0.0000000, sometimes I've lost track, 523. Is that small? That's really, really small. It's even smaller than that 0.0018. So yes, we have proved something with a high degree of certainty. If these p-values are above 0.05, it means that variable is probably not significant and you want to eliminate it. Certainly if it's 0.10, you want to eliminate it. Why? We don't want any extraneous variables in our equation in case, when we're making our forecast, it takes on a bigger or smaller than normal value, and it's going to skew my forecast and make my forecast less accurate. So step one was throw all the variables you think are related to what you're trying to predict in a hat, run regression. Step two, look at the p-values. Eliminate any values that are bigger than 0.05. Are any of these bigger than 0.05? No, everything's good. It means our equation is good to go. What is our equation? It's under the coefficients column, right here. Our equations is right here. Okay? The equation is forecasted cost of production equals 3, my constant, my intercept, plus 3 plus 2 times X, where X is the quantity produced, is my forecasting equation. My forecasting equation is 3 plus 2X. So where is my, going back to my example here, wrong way, sorry. So at this point, I can say, okay, my best guess, forecasted cost next week, when X is 4.5, is 3 plus 2 times X, or 3 times 2 times 0.45. My best guess is we're going to need $12,000 to run the business. My best guess is $12,000. So you go into your boss and say, boss, I know you scoffed at my C- in statistics, SOM 120, but I learned a lot. I had a weird prof. He hated his brother-in-law, made up these weird problems. He collects fossils. He plays poker. He's just a weirdo all around. But I did learn a lot, even though he only gave me a C-, because he didn't like me. But I learned a lot. Oh, and I predict we need 12,000 bucks to keep the business open next week. And your boss says, hey, fabulous. You're telling me I need exactly $12,000. And I said, no, I really didn't say that. And the boss says, what's the probability we need exactly $12,000? And you say, roughly 0. What's the probability you need 12,000 or less? 50%. 12,000 or more? 50%. We got a bell-shaped curve. We sampled over 30 or more. We got a bell-shaped curve centered at 12. Bell-shaped curve centered at 12. It's our uncertainty regarding exactly how much cash we need. All I got to do is tell you what the shape of this curve is, and you know everything there is to know. And the shape of that curve is right there. Is the shape of this curve right there. The standard error, or the standard error of the estimate, is the shape of that curve. That's my standard deviation, if you will. I don't like to call it that because we got too many standard deviations around. So I call it the step size for our forecast. Yes, sir.
Sorry, I'm confused with the significance of if I were to do that, like 50% below 12 or 50% above 12?
On any normal curve, what's the probability we're at the center or less? 50%.
So like, if your boss heard that, I feel like he would be very impressed with that.
No, your boss wouldn't be very impressed with that. All you can say is there's no chance it's exactly 12, and a 50% chance I've underestimated, 50% chance I've overestimated. Your boss is not impressed at all. I wouldn't ask for a review right now. But after you say, okay, boss, I'm 68% sure it lies between plus or minus one step of 1.67. Okay, again, the 1.67 is right there. There's your 1.67. That's where we get it. That's what you do all your confidence intervals after you've used regression to forecast. Comes from there. I'm 68% sure it's between $10,330 and $13,670. I'm 95% sure it's between $8,066 and $15,034. 99% sure between there and there. I want to be 97.5% sure I got enough money. 15,340. 95, 2.5% to the left, 2.5% to the right. Okay, so I'm 97.5% sure. If we have 15,340 bucks, we got enough money. All right, so I'm able to answer all these nifty questions and wow my boss and connive him or her into giving me a raise because I kept my notes from regression after my SOM 120 class was over. All right, so far that's what we need to look at. We need the p-value column. We need the coefficient column to get our regression equation. We need the standard error row up here to get the step size of my bell-shaped curve when I'm done. Okay, let me just mention the R squared here, and that's really all you need to know. I don't know why Excel gives you an R square and an adjusted R square. Just give me one. And probably the more correct one is the adjusted R square. What is the adjusted R square? Give me a rating for this regression forecasting equation. On a scale of 0 to 1, give me a rating. Or on a scale of 0 to 100, give me a rating. The rating would be 65. What does that mean? It means 65% of the variation in production cost is explained by knowing the quantity produced. Most of the variability in our production cost is attributable to the quantity we produce. 65% of the variation in whatever it is we're trying to predict, actual cost, is explained by this regression equation. Perfect would be 100, you know, worthless is 0. Okay, we take the best R squared we can get. Is this perfect by any means? No. I mean, we've explained 65% of the variation and we didn't explain 35%. And it's random. But, you know, we live in an uncertain world. When I did my doctoral dissertation, I got an R squared of 0.50. Okay, gee, that wasn't very good. Well, it was better than anybody done so far. And I was predicting the value of offshore oil leases, you know, 4 miles out in the ocean. So it was, you know, it was an improvement. We go with our best shot. If we got uncertainty, yeah, welcome to life. That's all you need to know. That's it. You now know regression. There's a whole bunch of other stuff here, okay? Don't worry about it. Okay. If you take the square root of R, you get what's called the multiple R, which is just the coefficient of correlation. It's called the coefficient of correlation. Let's see, anything else worth noting here? Okay, let me just go over this one thing, and then that's all I think you need. Well, right now, you know everything you need to know to get 100% on the problem on the exam. What is the 3 and the 2? The 3 is our best guess as to the fixed cost. Okay. And the 2 is our best guess as to the variable cost per unit. For those of you accounting majors, when you sit for the CPA exam, gee, guess what technique you're going to need to know? Regression and correlation, because it's the #1 means of estimating fixed and variable cost. Yes, sir.
Like if this was based on a long-term model, would you not have fixed costs?
Okay, and supposedly, according to economists, in the long run, there are no fixed costs. So that is true. It's a short-run model. All right, so, okay, what's going on here? Are our fixed costs exactly 3,000? No, I have uncertainty. Okay, you got a bell-shaped curve. You know the punchline. Centered at 3, your best guess. What's the shape of the curve? There you go right there. There you go right there. Give me a 95% confidence interval. Huh, there you go right there. I'm 95% sure that the fixed costs are somewhere between $1,200 and $4,700. My best guess is $3,000. Okay, is that exactly plus or minus 2 of these steps? No, because we round it off. We're not doing it exact. Our 95% is not quite exact, okay, but it's good enough for most instances. The variable cost per unit, I think, is $2 a unit. Is it exactly $2 a unit? No, you have uncertainty. You got a bell-shaped curve, centered at 2. What's the shape of that curve? There you go. Give me a 95% confidence interval on where our our variable cost per unit are. I think they're $1.44 to $2.56. Almost exactly plus or minus 2 of those. All right, so I explain these things in detail on the handout there, so you can look at them at your leisure. And let's just do a quick review of what we did. We performed regression on Excel and we included all possible relevant independent variables. We look at the p-value and get rid of any variables that are greater than 0.05. We rerun regression and eliminate them. We write out the regression equation, we plug in our values, and we make our forecast. Then we do a confidence interval around our forecast using the standard error of the estimate. And then we review and interpret R squared. Easy peasy, huh? Good. All right, so what is regression and correlation? We're looking at the relationship that exists between two or more variables. The ones we know are called the X's, or the independent variables. I knew the quantity produced because I schedule it ahead of time. The one I don't know is the Y, the one I'm trying to predict. So we pick X's that we know in advance or control. Okay, so we find the equation that exists within our sample, and that is the equation that we are going to use, assume is close to the one that exists in the entire population. The X is sometimes called the explanatory or predictor variable, and the Y is sometimes called the response variable. Okay, so we have a population. What's new and different is our population consists of the answers to two or more questions. Before we were just asking one question, you know, like how many miles does Uranus get? You know, that was one question. And now we're asking two questions. We ask the question, for this month, how much did it cost and how much did we produce? And those are pairs of X's and Y's. And if we ask another question, you know, like, you know, how many workers did we have or something like that, then that would be another X. And we're trying to estimate the average relationship that exists in the population. The constant is called the intercept, and it's the value when X equals 0. And the slope is the value for every value of X that goes up 1. This is our multiplier. The slope is the multiplier for what it is we're trying to forecast. If you get a perfect linear relationship, then what? Our R-squared would be 1. And here's the symbol for our standard error of the estimate. The fourth thing we did, it's called S sub E, is the standard error of the estimate. That's our notation for it. If we have no points lying off the line, then we'd have a perfect predictor. Very seldom in the real world do you get that. We're stuck with good predictors, good linear relationship. I plot that data, that's a good linear relationship. The points are clustered around a to be determined line. We use something called the least squares method, which says, give me the line, out of the infinite number of lines I can put through this data, give me the line that has the smallest squared vistas of data points off the line, smallest squared vertical distance of points off the line. And that's the one regression runs for you in Excel. Excel does least squares regression, most common one. So we got a 1.67, and we got an R-squared of 0.65 in the ones we did. Here's the one my brother-in-law suggested. My brother-in-law suggested this X. He said, we should choose this X because it's related to Y. Is that related at all? No, it's a shotgun blast. What's the best fit of the data through this line? It's a flat line at 9, the mean. The mean of the Y's is 9. That's the best we got. What is the R-squared? It's absolutely worthless. It's 0. And what is SE? SE is 2.80. What is 2.80? It is the sample standard deviation of variable Y. That's the variability you started with. When you're trying to guess Y, that's what you're dealing with. That's what you got to overcome. All right, we're almost done. Hang in there. All right, so if we get something like this, What's that? That's a good exponential relationship. So see how we keep going up more and more and more and more and more and more. We're increasing at some rate. The rate is, we have a rate here that's going up and up and up. The percentage is going up and up. Percentage is constant, but we're going up and up and up because the values are getting bigger. Okay? You hear a lot about exponential growth these days. This is the type of curve you get. If you got one like this, your product is probably in its mature stage in its market. So we're ever decreasing. The amounts of increase are less and less. It's still increasing, but at a reduced rate. That's called a logarithmic relationship. All right, what can I expect? 3 weeks from today? 4 weeks from today, when we have our final exam. Problem 1, a regression problem. I might even use this very problem and just change some of the numbers. This is how easy it's going to get. Okay? I give you a printout, and I ask you some questions. Our example is, let X be advertising and expenditures in thousands of bucks, and let Y be the sales of potato chips in thousands of bags. Let's just assume it's the little small bag. Well, that sell for like $1 each. So I want to predict sales. And, it's like a small little company, a little designer potato chip. I run regression. And here's the regression result. Step 1, what do I do? Check out the p-values. The p-values are the chance that these variables are not significant. The chance that these variables are not significant. They don't significantly predict sales. Both of those are exceedingly small, way below 0.05. It means what? Our regression equation is good to go. Our regression equation is 300 plus 5x. Your x is going to be 80. You're going to spend 80,000 on advertising. Plug in to your formula. We predict sales will be 700,000, 700 in this case, in thousands, bags of potato chips. Will it be exactly 700,000? No, it won't. Give me a range that's 68% sure, a 68% confidence interval. It'd be 700 plus one of those right there. That right there is our value, right there. Right there is our value. Come on. Well, 40. So it would be 700 plus 1 times 40. If you want to be 88% sure you got enough, how much should we stock? Okay. It's a regular old bell-shaped curve. I just use regression to get it. See, the end of all of our stories were always the same the last half of the semester. We ended up with a bell-shaped curve. We do estimation, we got a bell-shaped curve. We do hypothesis testing, we didn't draw the curve, but there's a bell-shaped curve there, and we're comparing a couple of results. And then we do regression, and there's a bell-shaped curve. It's just the theory tells us how to get there a little bit different. But once you got a normal curve, and I tell you the center and the shape, you can do any of them, just like you're going to, you showed me on the exam, or you're going to show me momentarily. And that's why it's so important to know the normal distribution. Give me the 88th percentile. Okay, go look at 0.8800 on the tables. Let's do a one, maybe our next to last time. Find me the 88th percentile. Ooh, that's close. There we go. 1.18 steps. We'll do that. 1.18 steps. So start at 700, walk 1.18 steps to 400. Okay, on the average, each dollar spent on advertising generates sales of how many bags of chips? The interpretation is, let's spend $1 on advertising. What would we get? 305? Let's spend $2 advertising. What do we get? 310? Spend $3 advertising. Oh, 315? Each dollar of advertising generates $5 sales. This is how we evaluate the effectiveness of our sales group, our marketing people. Okay. Can I afford to make $5 in sales from $1 spent on advertising? Depends on the product. If it's a high profit margin item, sure you can. Laughing all the way to the bank. Is potato chips a high profit margin item? Yeah.
Wouldn't either way still be worth it if you're paying $1 and getting 5 back?
I'm getting 5 bags of sales, not dollars. These are bags of potato chips sold. So if they're $1 each, we're spending $1 to get $5 in sales, in revenue, not profit. If it was profit, then yeah, sure. All right, is potato chips a high profit margin item? Hello, people. Earth to class. What's the cost of goods sold on a bag of potato chips? What's it got in it? A quarter of a potato? What's that? 2 cents. Grease, salt. What do you have? 3 cents. Air in the bag. Bag it. 5 cents. Get it out over here to the whatever that dump is we all eat at. Evergreen, or what is it? A Harbor Grill. Get it out the Harbor Grill. Another 20 cents maybe. Most of it's transportation. What are we at? 30%? Can I spend $1 to make 5 times 70% profit margin? 350? Oh yeah, laughing all the way to the bank. Great. See how this stuff all works? All right, that's it. That's all, folks. Try for next time when we'll go over the case study. Here's 3 samples from the case study, page 35, 36, 2, 3, and 4.